Good morning, everyone. Our second lecture this morning is the second in the mini course on Tame geometry and Hodge theory, being given by Bruno Klingler. Bruno, the floor is yours.
Thanks a lot. Okay, so yesterday I recalled the basics of minicourse structures. And the goal today is to give some applications. So I was planning to do much more, but as I spent a lot of time on basic results yesterday, I decided to focus on definability of Pila-Wilkie, which is more the topic, and that will be used also by Jacob in his lectures this afternoon. And so basically, I won't say anything about atypical intersection and functional transcendence, which was mentioned by Boris. So basically, the zip-up conjecture, of which the underworld is a special instance. And so what happened is that I generalized those conjectures to the setting of variations of our structures. And it was proven in the pure case by Jacob and Baker. So I won't have time to say anything about this. So for people interested in this functional transcendence business and atypical intersection, I refer to my mini course in IHS, my last mini course in IHS last spring about this. Anyway, so today I talk about applications to Hodge theory. Okay, so why should the algebraic geometer get interested in minicourse structures? So basically because it provides two nice ways of proving algebraicity results. So I will mention the first one, although I will not use it, but because this is used also in this functional transcendence business. So the first one is the Diophantine criterion. So it's kind of nice. So usually in Diophantine geometry, you start with an algebraic bar to find a number field, and then you try to count points. So this is the kind of typical example. And Admissibility will start completely differently. You will use counting points to prove that something is algebraic. Okay, so what is the theorem? The famous result is due to Pila-Wilkie. And it says the following: suppose that you start with some subspace of Rn, and which is definable. So now definable means definable in some minicourse structure, like one of those that I defined yesterday. And suppose define the algebraic part of the alg, as being the union of all positive dimensional semi-algebraic subsets of Z. Okay? And now the question is to know if this is big or not. And the claim is that, well, to do that, it's enough basically to count rational points of bounded height. Namely, you have the following result. Then for any epsilon larger than 0, there exists a constant C epsilon, which is positive, such that if you count the set of points Z in Z minus the algebraic part, intersecting with Q to the n, or you can replace Q with a field, number field, then you count them. So you need a boundedness assumption. So you fix the height smaller than some number t. So if you count those points of height at most t, and then it has to be smaller than c epsilon t to the epsilon. In other words, if you have a subset such that when you count the number of rational points of height of bounded height t, and it grows faster than a polynomial in t, then this means that it contains positive dimensional algebraic subset. Okay. So maybe I just give the prototype of such a statement. So can we see? Yes. So the typical example is the following. You put yourself in a box 0, 1 cross 0, 1, and then you draw some real analytic curve in it, C. And then the result is that if you take the intersection of C with Q squared, so count a set of points such that height of Z is smaller than T, then if that set is big enough, it grows faster than a polynomial in T, and in fact this curve has to be real algebraic. Okay, so that's the conclusion. So this is an extremely strong Darf-Einstein criterion to produce algebraic sets. So now, what is the second kind of algebraicity results? Well, it has to do with complex geometry, so even complex analysis. So, what is the motto here? The motto here is that Tame geometry, so omnimal structures, they are not compatible with the pathologies of complex analysis.
Question?
So let me give an example in dimension 1, complex dimension 1. What is the lemma? To give you some feeling of what happens. Suppose that let F map from the function disk to C, which is holomorphic. And of course, you know that you can have an essential singularity at 0. But suppose that this map is also definable in some omnimal structure where you think of this as being R2, and this is semi-algebraic inside R2. Okay? So this makes sense to say that this is definable for some omnimal structures on R2. Then 0 is not an essential singularity. In other words, your map F has to be meromorphic. Okay? So it really tells you that this definability assumption kills the potential pathologies of your map. And the proof is kind of nice. So I wouldn't say it is trivial because you need the great Picard theorem. So let me maybe sketch, give the proof of this lemma so that you get an idea of kind of apply this technology. So otherwise, this map has an essential singularity at 0, then you know that 0 cross C has to be contained in the closure of the graph of your function with an essential singularity, and in fact is in the boundary. So this is the great Picard theorem. But then you are already done, because then this means that the dimension of this boundary of the graph, so dimension of this set, is the real dimension is 2, but this is also the dimension of the graph. So this is a contradiction to the definability assumption of F, because the graph has to be a definable set in some linear structure, so its boundary has smaller dimension. Okay, so we give you some feeling of what happens, and let's go to a higher dimension. And this we will really use. So in complex analysis, there is a classical theorem due to Riemann-Einstein. That says the following. So suppose you are in the following situation. You have a complex manifold, and then you remove a closed analytic set. Closed. And then inside this, you take X, which is C analytic and irresistible. And then basically the question is, what can you say of the closure of X inside S? Is there any chance that this guy is complex analytic? So of course, in general, this is not the case. But then there is this theorem of Ax-Schanuel tells you that under some tameness assumption, and this tameness assumption here is just that the dimension of X is strictly smaller than the dimension of the set that you have removed. Then the closure X, the topological closure, is a closed analytic subset of S, the analytic closed, of the right dimension, right? So, and with dimension of C being the dimension of X. So you can extend X through the singularities E. Okay. So now there's a version of this theorem which is due to Peterson and Starchenko, and which says the following. Suppose now that S, your complex manifold, is also definable in some omnium structure. Okay? And suppose that the C analytic set is definable here, then you remove this dimension assumption and you have the same conclusion. So as a corollary, you see that you get a version of Chow theorem, but without any projectivity assumption, just a definability assumption. So corollary. And then I think in the next lecture, Jacob will spend quite some time generalizing this to an omnium GAGA. So this is due to Polarization and Starchenko. And then it says that suppose that you are in this situation, you have S, an algebraic variety, and now you take the complex analytic space in it, associated to it, and you take a closed subspace, and you can prove that you assume that X is C analytic closed. All right, and what you would like to conclude is that in fact X is algebraic inside S. So S here is the projective of C. You can just think that S is C defined space. Let's put. Then, if you just put the assumption that this guy is definable, then X is algebraic. Okay. And the proof used this result to go back to the classical Chow theorem, right? You extend X to the singularities when you compactify S into something projective. So another remark is that this was proven in the semi-algebraic case by Fortuna and Wojciechowicz in the 80s, I think. And this is not really difficult. You can also apply just a version of Bishop theorem if you want. That's another way of seeing it. All right, so this is an extremely useful algebraicity statement, and now I turn to Hodge theory. So what I want to explain now is how you can maybe have a better view of some results on asymptotic theory of the generation of Hodge structures using this omnium business. Although I have to say that I'm still not completely satisfied in the sense that we are using results proven through classical analysis, and this is not completely internal to the theory, but still. Okay, so maybe so I'm expecting most of the people to be very familiar with Hodge theory, but maybe I will fix some notations nevertheless and recall some stuff. So suppose we work over a point. So what is Hodge theory at the origin? So this is the following definition. So this is just a semi-linear gadget encoding a lot of information associated to the common G of algebraic varieties. So you fix a ring, and let's say Z, or you fix Q, or R, and then what is the mixed R structure? So this is a triple. So what is this triple? This triple is just, I will denote it by V, this is VR, and then I will have an increasing filtration on VR and a decreasing filtration on the complexified space, satisfying a certain number of compatibility conditions. So what are those things? So VR is an R module of type, and W is an increasing filtration on VR. And this is called the weight filtration. And F dot is a decreasing filtration on VC. By definition is VR conserved R by C, which is a finite dimensional vector space, complex vector space. And this guy is called the Hodge filtration. So now, what are the requirements on those data? Well, such that when you take the Gre with respect to the weight filtration, so this is Gre L of the R. So this is an R module of finite type, and I can add that this is a pure R Hodge structure of weight. Yeah. So what is such a thing? Well, this is the same thing as a mixed one, except that now everything happens only at one weight, namely L. So this is just a requirement that when you take the induced filtration of F once it's graded, then you get the graded F. Let's put it Q F bar of that space. Is equal to 0 when P plus Q is different from L. Okay? So this is this kind of double filtered R module, except one filtration is really on the R module and the other one is only on the complexified thing, and this is the only conditions that you are fixing. So in particular, if you are pure, this means that this guy is direct sum of HPQs with the usual compatibility. This is equivalent, okay? So there is a natural notion of morphism. There are just the natural one, namely a morphism of R modules preserving filtrations. And there is an important notion, which is the notion of polarization. So we'll say that V is graded polarized. Or polarizable. Each of the pure Hodge structure associated to them, so those guys here, is polarizable. So this means that there exists a polarization form. So what is this? This is a symmetric, -1 symmetric, -1 to the L symmetric form from that guy. -1 to the L symmetric. linear. And then there is a positivity condition that I will not write because most of you know it and it's fine. Plus positivity condition. Positivity on the associated Hermitian form. So the associated Hermitian form is not positive definite, but when you twist it by the Taylor operator, it becomes positive. So that's the basic data. I hope most of you know that. So why is that interesting? Well, the idea is that with this kind of gadget, you get a pretty good information about algebraic variety. So this is some kind of linearization procedure, right? So we prove that if X is any kind of algebraic variety over C, not necessarily smooth, not necessarily proper, then if you take any group of cohomology with Z coefficient, let's say, then it carries the factorial with respect of morphism of algebraic varieties, the mixed substructure, and which is graded polarizable. So from now on, all the mixed substructure will be graded polarizable. So this is the main reason why we get interested in this kind of linear algebra gadgets, is that if you have a Torelli theorem, it will tell you that you can recover X just getting those mixed substructures. All right, so now this was the story of a point. This is just a vector space with these two filtrations. So now let's do the theory of a base. This part of the theory, the smooth part. So suppose you have a family of algebraic varieties. So S is quasi-projective and smooth. And you're assuming for simplicity that this morphism is smooth or equisingular, let's say. What I want, so I'm not assuming that the morphism is proper, so of course, what I want is that locally the fibers are diffeomorphic, so that I get really a local system when I look at the cohomology. And so out of this, what do I get? Well, I get something that will be known by V. So this is first a local system, finite rank local system on the analytic space of S, which is fixing a degree R, N, F, and this part Z. So the fibers of local system are just the cohomology of the fibers in degree N. Then associated to this are the holomorphic vector bundle. I have the corresponding flat connection, so the Gaussian connection. Then I'm using now this result of the link filtration on V, which is the Hodge filtration. And in fact, this defines a holomorphic filtration by vector subbundles. And I have the wave filtration on my local system coming from the wave filtration on the fiber, and this is really locally constant. So, and moreover, there is some compatibility condition between those data. Maybe when you apply a nabla to FP, then FP is not stable, it's not a flat subbundle, but it's shifted by at most 1. So this kind of gadget is what is called a variation of mixed Hodge structure. And then this is graded polarized, so which means that you have a family of such forms on VZ, in particular those are flats, with those positivity assumptions that you have to force. And okay, so at that point, so this is the notion of a graded polarized Z variation of mixed Hodge structure. So this this notion is not exactly the one we want because it has bad property in general if you look at infinity in S. So if S is not compact, which is the majority of cases, then you would need some strong assumptions about the degeneracy of those data at infinity, and this is the notion of admissibility. So in my geometric case, B is admissible. So I will not write the precise technical condition, but this controls the degeneracy of the triple nabla W and F near let's say you take a compactification and you look at what happens at the boundary. Okay. So just a remark is that this is an additional condition that you have to put on your general abstract gadget variation of our structure. In the geometric case, this is automatic, and this is also automatic in the pure case. So now we want to study this kind of gadgets. So basically understand the cohomology of families of algebraic varieties. All right, so the first claim is that there is a nice way of describing such a variation of a structure. So very polarizable Z variation of mixed structure on S, and there are the same thing as giving yourself a period map. So what is a period map? This is a holomorphic map, so this is in the complex analytic category, to some classifying space of Hodge structures, of mixed Hodge structures. Let's call it M over gamma. So let's say immediately that the main problem with me is that this classifying space is not algebraic, and this map is in general absolutely not algebraic. So there are some particular cases where this guy is a Chinois variety, basically when all the pieces in your Hodge structure are degree 1 or 0. But otherwise, it's really kind of absolutely not algebraizable. And so let me say what is M. M is what's called a very polarized domain. Okay. And it classifies the possible Hodge filtration on a given VC or a given let's say, well, I will fix VQ maybe. VQ, you fix the possible weight filtration, you fix the flat polarization, QL, and you ask and fix Hodge numbers. So the HPQs are exactly the dimension of this greux P, greux Q for F, a bar of greux P plus Q W, BC. These are the Hodge numbers. So you just want to classify all the possible Hodge filtrations that will give you these Hodge numbers with respect to this fixed rational vector space, this fixed weight filtration, and this fixed polarization. Okay. So so what happens is that, well, if you have your variation of structure, when you lift it to the universal cover of S, then the local system is trivialized. This gives you this guy here, this vector space. Your local system becomes just S tilde times VQ, and all this is trivialized because this is also local. And then at the level of universal cover, you just have to describe how the Hodge filtration varies. And as I said, the Hodge filtration varies holomorphically, so this gives you this map from the universal cover, if you want, to M. And then there is some monodromy phenomenon. So when you go back to S tangent, you have this solution by gamma, which is basically the monodromy. So what is important for us is that although in general M mod gamma has absolutely no algebraic structure, then this is closely related to algebraic geometry through group theory. Because this M is a homogeneous space, and so I want to say a bit more about this. So what is the structure of this M? Well, M is parameterizing hash filtration for on each, in particular, on each of the greux of those W. So it projects onto the product of all the MK, which are the corresponding hash filtration on the greux WK of that space. Okay. So here I'm just parameterizing the underlying, I mean, the quotient pure hash structures. All right, so the structure of that guy is well understood. These are classical P domains. They are open bound open subsets in the product of flag varieties MK hat, which you obtain if you forget the polarization, the positivity condition on the polarization. Okay. All right, and inside here, so now where are the groups? So here you have the action of groups that we denote by H, underline, and the set of points, of little points, is just the product of the automorphism group of each of the polarization forms. So it acts on that product here. All right, so here you have an action of the corresponding set of complex points. And those two actions are transitive. So this is a product of flag varieties, and this is a product of open in a flag variety, which are orbits of a real group. All right, so that's the first thing to understand. So now M is embedded exactly in the same way here inside, if you forget the graded polarization condition, inside the compact dual. And here we call just G the preimage of that group in the automorphism of V. So in other words, this guy is a reductive part of a group. So basically, G of C is unipotent radical times H of C. Okay? And again, this guy acts transitively. So, okay, on that space. So all the actions are transitive here. And this is where, here in the mixed case, the situation is a bit more complicated, because you could hope that the real points here acts transitively, but this is not true. What is true is that there is an intermediate group which is called that I would call G that acts transitively here. So now what is this group G? Well, this group G is nothing else that, so you have G of R, which is contained in G. So this is G of R times the unipotent radical of G of C. And this is contained in G of C. Nevertheless, this group is a nice semi-algebraic group, if you want. And finally, what is gamma? Well, basically, gamma is G of Z. So sure, at least it is contained in G of Z. Okay. So let me see what time. So in fact, just one small remark is that. So this is a description in terms of period maps of variations of mixed structure, and one should refine a little bit construction, meaning we replace F on VC, we replace it by F on all possible types of powers. So we don't want to only classify Hodge filtration on VC, but the induced Hodge filtration on all possible powers of V and dual. It's natural if you want to do group theory, because then everything becomes Tanakian. All right, and if you think in terms of Hodge theory, in fact, Hodge structure is uniquely determined by its Mumford-Tate group, which is a group of invariant Hodge classes in all such tensors. So in fact, what you want to classify is not really this Hodge population in DC, but the non-vortex group. Okay? And if you do that, well, you will define that space M. It will go in a very looking similar space, but where G, the group acting here, this algebraic group, will be replaced by the giant non-vortex group of your variation. And so I will denote the space that you get by D rather than M. So it will play a role, but I don't want to say too much about this. So let me emphasize again that the main problem is that, and so M mod gamma by D mod gamma, and that this D mod gamma is almost never algebraic. All right. So now that we are here, what is the main result that I want to state now? It's the following, that so with Ben and Jacob, in the pure case, and then Ben, myself, and Rinbar, myself, and Jacob. So this is published, and this is on the archive. The theorem is that although D mod gamma is almost never an algebraic variety, it has a canonical RH structures. So mixed Hodge varieties D mod gamma can be functorially endowed with natural RH structures. But there is a natural atlas of charts of D mod gamma with value in Rn and change of coordinates which are semi-algebraic. This atlas of charts is finite. So, and the functorially is very important for what follows. This means that each time you have a morphism of the form D prime mod gamma prime to D mod gamma coming from Hodge theory, which means also that it comes from group theory in some sense, this map is RH definable. So this is not an algebraic map, but it is semi-algebraic in the sense of that structure. And the second thing is that if V is admissible, greatly polarizable variations of fixed structure, then the associated field map phi S from Sn to D mod gamma is Rn X definable. This is the main part of the theorem. So it says that if you endo Sn with its canonical Rn X structure coming from the algebraic structure on S, so the one that I told about yesterday, and if you endo D mod gamma with this RH structure and you extend it to an Rnx structure, then this map is Rnx definable. In other words, in this finite atlas of charts here, if you write this field map in this finite atlas of charts, then you have only to use the real exponential and some real analytic functions restricted to compact sense. So it says that field map, although it is a transcendental map, in some sense it has the same geometry. So I should make a few remarks. So there are some cases where D mod gamma is compact, in which case the theorem is kind of trivial, because in that case, in fact, if D mod gamma is compact, this means in particular that gamma does not contain any unipotent element. But Boyle-Mondromi theorem tells you that the Mondromi at infinity of this map is quasi-unipotent. So it tells you that in fact it kills the local pi1 at infinity. And so in that case, the map extends to a compactification of S to D mod gamma. So you have a complex analytic map between complex analytic spaces, but then you have them. Okay, so this is you are definable. So this is no problem. Another remark is that in the case where d mod gamma is algebraic, which means that basically the pure part is weight 1. Okay. So what I was saying, so this is the main theorem, right? So that we can handle d mod gamma with a natural RI structure, and that the PL map is always definable with respect to RNX. Okay? And then I was explaining that if d mod gamma is compact, this follows from Borel-Modromy theorem, because you kill the Modromy at infinity in that case, because gamma does not contain any unipotent element. And I was saying that if d mod gamma by accident is algebraic, which is the case where the pure structure is of weight 1, basically, then this map by Ax-Schanuel has to be algebraic, and then you recover an old result of Borel. All right, so now I want to talk about application of Hodge. So do you hear me now? This is okay? So what are the Hodge? So what is the Hodge locus for SV? Well, this is a set of points S and S, such that you have exceptional Hodge tenses. In other words, where some Hodge classes like here appear, but maybe in some tensor power of V and it's 0. Okay. And so, of course, if you believe in the Hodge conjecture, each time you see a Hodge class, this means that in the background there is some algebraic cycle, and algebraic cycles have the nice properties that you can do them together because you have Hilbert schemes. And so this means that, as remarked by Tame a long time ago, this means that this Hodge locus should be a countable union of algebraic vertices. Okay. And in fact, this was proven by Kaplan and Kaplan in the pure case. By Rosnan, Stein, and then Rosnan, Gerstein, and Schnell in the mixed case. So they did the case of normal functions, extension minus 0.0, if I remember correctly. So this is a pure case. And then this is a mixed case. That you prove that this Hodge has V is a countable union. And once you have this theorem, in fact, this is a direct corollary if you use a better synthetic code, because here's the proof. You have your analytic map, which is definable, and inside d mod gamma, you have a union, a countable union, parameterized by subgroup of the joint Forte group, and maybe by elements in G of Q, which are your Eke correspondences of some Eke translate, let me denote them by G, of some d prime mod gamma prime. So this is not really group action, this is a correspondence, but nevertheless. So you have this countable union of subspace in d mod gamma where the non-Forte group becomes smaller. So because of the first part of the result, each term here is definable. And now the Hodge locus is nothing else than the preimage of that thing here. So you have a Cartesian diagram like this, and this is the fiber product. So you see that a component, an analytic component here is just a preimage of such a thing by your period map. But now by the second part of the theorem, as this guy is definable, the preimage of each of those guys is definable here. But this is inside S, which is algebraic. So we have something definable inside something algebraic, and this is complex analytic, of course. Then it has to be algebraic. Each component has to be algebraic. Okay. So once you have this theorem, you see that those very nice results are a direct consequence of it, and better than Starchenko. I think this is quite nice. I'm lucky. So in the next lecture, Jacob will also explain another application, namely that basically the image of this period map has a natural algebraic structure. And this is where we need this minimal GAGA to do this. So now what I want to do in the remaining time is try to give an idea of how to prove this kind of thing. So I will start with the pure case and then move to the mixed one. So pure case. That's too bad. I erased the theorem. So I'm sorry. So the first thing I want to prove, I want to endow my d of gamma in the pure case with a RH structure, right? Now what is D? This is D. We saw that this is D of R mod M. So G is some semi-simple group, and M is compact. And so yesterday we saw that this kind of quotient has a canonical RH structure. Okay, because this is given by an equivalence, a proper equivalence relation. Okay, so now gamma inside here, well, basically you can take G of Z, acts properly discontinuously because M is compact on D. And so, by the result about étal equivalence relation, étal definable closed equivalence relation that I mentioned yesterday, we are reduced. We have to find a nice fundamental set for gamma, so enough to construct an RH definable fundamental set F for gamma inside D. Right? This is what I explained yesterday, that each time you fix such a definable fundamental set, then it can do your quotient D mod gamma with some minimal structure. And basically, well, in that case, this is classical reduction theory. There is a notion of Ziegler sets, and so you can take F as the finite Ziegler sets C in G mod M. So maybe I will call briefly what it is. You write G of R, you decompose it as a product. So here is a parabolic subgroup, and here is a maximal compact subgroup. So this is maximal compact. In particular, it contains M. What is N? Well, this is a unipotent particle. Sorry, I think I used U in the general case, but okay. And what is A? Well, this is a maximal split R torus. Okay. Then what is the Ziegler set? Well, basically, Ziegler set, or let me just write F. You take a bounded subset inside N. This is just any kind of bounded subset. In your maximal split R torus, you take the positive cone, A plus, let's say. How do you denote them here? A plus, maybe depending on some parameter T, but this is not very important. And well, you can take the full K, which is compact here. So basically, you look only at what happens in some flat directions given by A, and there you take a Weig number. So let me quotient by V to see that guy inside by V by M to see that guy inside G of R M. So maybe to make things clearer, I use the example of SN2. Right? So if G is equal to SN2 R, then in that case, G will be a Poincaré graph plane, and G acts transitively on this. then you write this group as being said. The composition is exactly this one. So these are this is your n. Here you have exponential t, exponential minus t 0, 0. And your compact group is a circle, so cos theta sin theta minus sin theta cos theta, right? And what is the Ziegler set? Well, if you choose a compact, so you just choose a compact interval where x is moving, so you recover the following picture. Here you have minus 1/2 and 1/2, and your classical, minus 1 and 1. The classical fundamental set for the action of SL2Z would be that guy. This is a fundamental domain here. So your F will not be exactly like this, but it will be something like that, where you can choose the size here of this interval. This corresponds to this parameter x. So this is easy to define. What is not completely easy to, so this is the proof of one, the existence of this Hodge structure. What is not completely easy is to prove that this is factorial. So what you have to prove is that if you have G prime inside G coming from a morphism of Hodge structures, then in fact you map one Ziegler set for G prime inside finitely many Ziegler sets for G, and this is not completely trivial. This was proven recently by Martin Orr. Okay, so now that you have defined this Hodge structure on the quotient d mod gamma, you have to prove that the PL map is RNX definable. So the thing you do is you embed S inside completion by the divisor with normal crossing. So this is take normal crossing. So this means that at infinity, basically, you have delta star to the r times delta n minus r inside delta n. So this is locally at infinity. And here you have this 0 coordinates. And so what you do is that you cover S by finitely many such guys. Varying the R, depending on where you are in the boundary. And so now what you want to prove is that your period map in restriction to such a thing is definable. So you have to show that if you look at phi from delta star to the R plus delta n minus R to d mod gamma is RNX. This is what you have to show, right, in terms of those coordinates. So now recall that here the structure is given by those Ziegler sets. And so you can contemplate the following diagram. You pass the definable structure here comes from the choice of the Ziegler set on the universal cover. So for simplicity, let me assume that R is equal to n. Right? So I don't want to get embarrassed. So here I now delta star to the n, I map phi to d mod gamma, and here I have d. So I lift everything to the universal cover, and I get this. And I have my phi tilde now, and I can choose a fundamental set of the same form. So a Ziegler set here. So just a product of band like the red one above. Okay, so this is this F8n. Here, this covers this delta star to the n. And basically now what we are reduced to is just to prove two things. We have to prove two things. Have to show that phi tilde in restriction to that guy F8n, to the Ziegler set, this product of bands to D is RNX definable. And B, right, this works because here this is really the exponential 2 by I. So your function is just the multi-exponential here. Okay? So if you have a coordinate z here, it's mapped to exponential 2 pi I z here. So I will call t the parameter, the image of z. So the first thing I want to show is that this phi in restriction to this fundamental set is definable because then this composite will be locally. And then you have the global problem that you want to be sure that globally the map is definable, which means exactly that you map this Ziegler set into a finite union of Ziegler sets here. So you want to show that phi tilde of this Ziegler set for on the left is contained in a finite union of Ziegler sets for D as defined above. So you are reduced to those two questions, and the question A, well, this is the direct corollary of Schmidt's nilpotent orbit. Because Schmidt's nilpotent orbit tells you that if you look at phi tilde of Z, then you can approximate it by a nilpotent orbit. So the I and I, where the Ni are the log of the monotomies, and the monotomy at infinity is unipotent, so those guys are nilpotent matrices. So you should be frightened by the X because there is some complex variable, and this is certainly not definable, except that because Ni is nilpotent, this is a polynomial, in fact. So we are good with this. And then the difference between this nilpotent orbit and your appeared map is just given by some function psi, which is holomorphic, but which extends to delta. So, and psi is a map from delta n to the compact duo, the hat, and this is holomorphic. So this map is a polynomial, and this one is in R1, because it extends to this compact thing. And so this tells you that this map is Rnx definable. You need the x because of this change of coordinates here. So this is one point. Okay, let me. I'm a bit short to do the mixed case, so if you want the mixed case, I can. But okay, so for B, the second thing that we have to prove, this is the crux of the proof, in fact. So we want to show this. So for n is equal to 1, this was proven by Schmidt as a corollary of his SL2 orbit theorem. The point is that we managed to prove it without the SL2 orbit theorem. It follows from estimates of Hodge, which are easier, which are already in the paper by Kishima. And the idea is that you embed your group G inside G and VR, and this guy tells you that you can map D to the space X, which is GLVR maximum compact. And what is this map? Well, this map is just the map which to a filtration associates the given Hodge norm at that point. And you notice that in fact it factorizes from geometry, but this is not really important. So here you have a surjection, but here is still compact. Okay, and now if you think in those terms, proving the definability, the fact that you are counting in finitely many Ziegler sets here, well, you can compose, right? So here you have F(n), and then you have your K map here, and proving that you are in finitely many Ziegler sets here, because of the functionality of Ziegler sets, it's enough to prove that this composite is in finitely many Ziegler sets. So this means that basically up to choosing a refinement, a finite partition of that thing, the Hodge norm can be put in Minkowski reduced form with respect to a flat basis. And this is what you have to prove, and this is exactly what the estimates on the Hodge norms give you. There is some work to be there. Okay, so can I take 5 minutes to finish with the mixed case, maybe, which is more recent? Philippe, do you think this is feasible, or you want me to stop here?
I think I'm taking over, but yeah, okay, 5 minutes, sure.
Okay, So in the mixed case, so the mixed case were frightening, and so we were kind of frightened. But now, what is the idea? So we have this D, and as I explained in the previous board, you have the associated PL domains for the graded, which are pure Hodge structure. So you have this vibration here. And on that group, there is a transitive action by this group G, and here you have this transitive action by this group H of R. Okay? So now, the idea is that inside this D, there is a better subvariety that we call dr, which corresponds, which is a closed subvariety here, which corresponds to the split, R split mixed-Hodge structure. So the one which becomes pure after extending scalas to R, okay? And this guy has a transitive action this time of G of R. Okay? So what is the basic point of, which will make the proof kind of easy, is that here there is a canonical refraction. So R is this is a semi-algebraic refraction. So here everything is semi-algebraic, and the refraction is also semi-algebraic, and this is G of R equivalent, which is important. And this is given by what is called Denis SL2 splitting. So in other words, there is a canonical construction to associate to any mixed-Hodge structure an R split 1. Okay? So now, what is the idea? The idea is that the idea is that it's enough to construct a nice fundamental set for dr under the action of gamma. So if R inside dr is definable, is an Ri, a fundamental set for gamma on dr, then F defined as being the image under this diffraction of Fr will also be. And so in some sense, we're reduced to contemplating those real split Hodge structure, and there the geometry is much simpler because now, as a GR space, GR is isomorphic to this product of DK. You have a natural splitting, and times the variety of possible splittings. So this is S is the variety of splitting. Of the wave filtration, and here this is the original guy. And this decomposition here is semi-algebraic, and again it is G of R equivalent. So here you know how to take a fundamental set, and here you just take. In fact, there is a transitive action of the unipotent radical. So R acts transitively here. So you take a fundamental set for the action of gamma on that variety of splitting, gamma intersected with U, sorry, and you multiply it with a fundamental set here. This provides you with a fundamental set in dr, and you put it back to D, and you get your fundamental set, which is semi-algebraic. And okay, the claim is that this works. Now, what about 2? So this was for 1. And for 2, in 1 minute, you are back to the same problem, right? You are looking at your product of bands, this Ziegler set for H to the n, and you map it to D. And again, we want to show that this is Ernst definable. So again, this is Schmidt unipotent orbit theorem, but now you have to use in a strong way the admissibility. Okay? To prove that psi extends. This is essentially the content of admissibility, that the psi that descend to the punctured polydisk extend to the polydisk. So this is Rnx definable, in fact, by Schmidt, important orbit, plus admissibility. So this is A with my previous notation, and for B now, you want to show that the image is containing infinitely many Ziegler sets. But again, by definition, this means that you are looking at the composite, because my fundamental set here is defined in terms of this refraction and taking a fundamental set here. So you have to prove that once you compose your PL map with this refraction, you arrive in a finite union of Ziegler sets here. Okay? And but now this guy, as we have said, this is this product of dk cross this variety. And so basically, you already know here by the pure case that you are mapped to a finite union of Ziegler sets here. So the only thing that you have to prove is that you arrive in a fundamental set here after projecting onto that factor. But here, this exactly means that you lie in a bounded set. And so everything follows in fact from this result of Postman and Bernstein. We did the job for us, namely they noticed that if you look at the composition Hn to S, well, to D, to dr, to S, then it is bounded on vertical steps. It is bounded. Well, let me just write not Hn, but really this product of vertical strips. Okay, and so this was proven by Grossman and Bernstein. So if you want, in some sense, this is also some kind of norm estimate. But did you see it from Kato Nakayama Uzui generalization of the SL2 orbit theorem? So again, I'm not completely satisfied with this proof, but that's another. At least conceptually speaking, I think it simplifies the picture of those degeneracy of PL maps. Although we still need estimates on norm, which are not purely given by O minimality. Okay, so I apologize for exceeding my time. I guess I will stop here.
Okay, so thank you, Bruno, very much. Thank you for the beautiful talk series. Yeah, so are there any questions? I think Mark, Mark, do you have a question? Oh, hi. Also, I can ask you a question to start the question series, which is, could you comment? We didn't really see Bruno.
Yeah, sorry. I'm trying to change the camera. Yeah. Okay.
Hi. Yeah. So, could you comment about the condition about non-integrability of the horizontal distribution? I'm not sure we really see that showing up, but it seems.
Of course, I should have a comment on this. And the comment is that all the estimates on the Hodge norms, they come from this negativity in the horizontal direction in the pure PL domain. Right? So if you had some positivity coming from a vertical direction, that nothing would work. So that's really.
Yeah, but what about the non-integrability? Is that related? Is there any kind of model theory aspect of that?
I don't have any good answer for this.
Mm-hmm.
I have to say. About the non-integrability, no, I don't have a nice. I think I don't have any nice answer about that. So sorry for that.
Okay. Anyway, so other people questions? Hello, everybody. I guess I can ask another question. I mean, this is probably a silly question, but one of the main questions is, can we sort of bound in some way the effective cycles that would have a given class? Do you think there's any prospect for minimality?
No. At least I don't see how. I don't have any guess about it. I don't see how you could
like bounding like some kind of height of special points and that kind of thing.
I have to say, I did not think too much about this, but the main problem being that I have absolutely no idea about what happens outside of the world of abelian varieties, right? For those heights of samples, so you can define them, but how they distribute, right? I mean, So when we deal with Andre Hort in general for Shimura varieties, we manage because we know what are those heights, basically.
Mm-hmm.
But in some sense, what is complicated about these special points in the non-abelian case is that we have basically no idea how they define over Q-bar, do you have nice Galois orbits, what is the size of the Galois orbits, what are the heights, all this is completely open because it depends on the fact that Hodge classes are absolute Hodge. So, in some sense, I would say that now the business is more or less stuck to understanding the points. I think we have, there are many results now on positive dimensional components of these hot blockers. But anyway, in the shadow, there is always a problem of components reduced to points. And this, we have absolutely no idea. So this is a big challenge, I think. So this omniable business is quite useful to deal with all positive dimensional problems, but for points, I don't have much to say right now.
Well, so let me ask if there are any further questions. I see some people have microphones jamming. Radu.
Can I ask a question?
Yeah, yeah.
Sure, Radu. Hi.
Hi. How about gluing these things together when you further degenerate or something like this?
I'm not sure I understand. What do you mean by gluing?
I mean, when you have a degeneration, like when you go outside.
Okay, so maybe this is something that I should say. In fact, these definable structures that we put, at least in the pure case, this is nothing else than Borel-Serre compactification, except that we realize it really semi-algebraically. The use of those Siegel sets, I'm just saying that, in fact, if I want to be faster, I could just say, okay, I put D mod gamma inside its Borel-Serre compactification, and now there is this theorem of Borel that tells you that this is a real manifold with corner. But the real manifold with corner is always definable in Rn, and so I would get the result in Rn. Here we do a bit better in the sense that we get really semi-algebraic, which I think is interesting for other applications. But the main point is that, as you mentioned, is that this Borel-Serre compactification, of course, it is related really to orbits, mixed Hodge structures that you would add at infinity to compactify your space. But there is no direct relation, as you know better than I do. There are some points in this Borel-Serre compactification which are good, which really correspond to some mixed Hodge structures that you would like to add, but there are some which are not. So in some sense, there is still something not really well understood. We are really using group theory and not purely Hodge theory. So, and in some sense, this is also, I mean, this is even more a problem when you deal with compactifying, starting with the mixed variation. Then the theory is even more degenerate and more complicated, and we do basically the same thing. We go through it just using group theory. So there are still, of course, I understand what you want to do. You want to try to exist in some space, but so it might be possible that smarter choices of fundamental sets or a smarter way of defining a non-minimal structure of the quotient more related to pure Hodge theory. That could happen. But,
and one more question. What about the difference between R algebraic and Rn exp that you had in your main?
Okay, so yeah, so you need this exp as I explained because of this structure on Siegel sets coming from. I mean, this comes from the universal cover. So in some way, you have to take into account this multi-exponential from the age n to the polydisk. And this is definable because you are restricted to bands. So this is what I should have emphasized. So at the level of the imaginary part, this gives you the full real exponential. Of course, you don't like the exponential 2 pi I x because this is a periodic thing, but you don't care because you're on a bounded set. So this is still in an So you really need the exp. There is absolutely no choice. I should have made the picture. I mean, already for SL2, you need the X. If you think how to define the structure, this comes from Polarization, so you have a circle at infinity. And basically, you need the X because this is this X that the circle to a point in the minimal compactification.
Okay.
Okay, so any further questions? I think maybe not.
Is admissibility equivalent to definability of the period map, or in the mixed case?
It goes very well together. And in some sense, yes, because you see, when here, the admissibility means exactly that when you write a Schmidt nilpotent orbit theorem, so you have this orbit and you have this side.
Okay, we don't see your platform.
Sorry. I changed the camera, of course. Yeah. Let's try the other one. Okay. What I was saying is that when you write this period map here, this phi tilde, then you have this fact up side, which descends to the punctured politist, and the entire business is to extend it, and this is really what admissibility tells you. So in some sense, I would say, yes, this is equivalent. At least this is equivalent to this A part. In some sense, this is the local business, and the B part tells you that moreover, you have a good compatibility between the Siegel sets. So this is half, I think this is half of the definability.
If I may add, Bruno,
sure.
We suspect, Abhishek, that they're actually formally equivalent.
I agree.
And we talked about this with Brosnan and Pearson and Baker, and it seems like maybe you can prove it, but there's some trickery afoot, so it's not totally obvious that you can do it. But it doesn't. It's not clear that it's so hard to prove an actual formal equivalence.
But you could a priori, I guess, expand RNX to a bigger O-minimal structure. So
you see, the problem is that there is no good notion of expanding in a bigger structure, because I would not know how to get the bigger ones than RNX.
Like the Pfaffian closure or something, I don't know.
Well, but in some sense, here, if you take the Pfaffian closure, I don't see a priori, in some sense, why this should help, because all the functions that you need are already there. So.
I see.
Yeah.
Thanks.
Welcome. Any other question? Maybe this is enough.
Okay, so let's thank Bruno again for nice talks.
Thanks.